Hi everyone, I'm Græsbøll Christensen of the Audio Analysis Lab at Aalborg University in Denmark, and I'm going to present a paper I originally presented at the Asilomar conference back in 2014, and the paper is entitled Pitch Estimation for Non-Stationary Speech. Okay, first an outline of my talk here. I'm going to give a bit of introduction and then talk about the signal model that this work is based on. Then I'm going to go into a bit of details about a method for finding the parameters of the model, and then I'm going to show some experimental results and then conclude on the work. All right, so in the past few years we've seen that so-called parametric methods based on the harmonic model can overcome the shortcomings of the traditionally used correlation-based methods. For example, they are more robust to noise, and you don't have problems with low fundamental frequencies and so forth. An argument against the parametric methods is often that the model is wrong, and in particular regarding the harmonic model, that it's wrong for non-stationary signals like speech, where you have continuously varying speech. And so in this paper, we propose a model called the chirp model and use it for pitch estimation in speech. And it takes the non-stationary nature of the pitch explicitly into account in the model, and then we use it as a basis for deriving an estimator for determining the parameters. And then in some experiments, we will investigate the properties and capabilities of the model and the estimator. And one thing we particularly are interested in is figuring out whether we actually need this kind of more complicated model for pitch estimation purposes. So for a segment of speech called xn, where n goes from n0 to n0 plus n minus 1, and I'll get back to why we choose this index later, then this harmonic chirp model is given by what you see here in equation 1 here, where you have a sum of L harmonics, and AL is a real positive amplitude here, and then we have these complex exponential functions here with theta L of n, which is the instantaneous phase of the what you call the alpha harmonic, and then we have some additive noise E of n here. This instantaneous phase here is a continuous function, and we here write it as a function of the continuous variable t. It is given by this expression you see here in equation 2, where you have an integral from 0 up to t of L times the omega 0 of tau d tau, and then you have a phase offset here. And so as you can see here, omega 0 of tau is now a time varying function. So this is essentially the function that we're interested in actually retrieving from a speech signal. And this phi L here is what you call an initial phase of the alpha harmonic. And if you compute the derivative with respect to time of this instantaneous phase function, you get what you see here in equation 3. And you can see that you end up with the frequency of the alpha harmonic here, omega L of t, being identical to L times the fundamental frequency. So so we get the result that we expected. And it should be noted here that in normal pitch estimation, it's often assumed that this pitch is constant within a segment here, which means that omega L of t is actually just equal to L times omega 0. And that's what you call the harmonic model then. Now, if we accept that the pitch is slowly and smoothly varying, then an appropriate model might be something like we have in equation 4, where omega 0 of t is equal to alpha 0 times t and then plus omega 0 here. And with the integral from before, we can see then that the instantaneous phase for the alpha harmonic is then given by equation 5 here, where we have a half times alpha 0 times L times t squared plus omega 0 times L times t plus the phase offset here. And then this alpha 0 is what we call the fundamental chirp rate, and alpha 0 times L is then the chirp rate of the alpha harmonic. And when we take this equation here in equation 5 here and plug it into the original model on the previous slide, then we get what we call the harmonic chirp model. And the problem that we'll now look into is the joint estimation of this alpha 0 and omega 0 from a noisy signal x of n. Okay, so the model we just seen on the previous slide in equation 4, you can think of that as a first order Taylor approximation of a more complicated, possibly nonlinear pitch function. And the shorter the segments, the more appropriate this model can be expected to be. And with alpha 0, this corresponds to a constant pitch, and this would be valid then for even shorter segments still. Now, in the literature, you can find an approximation that's valid when alpha 0 is approximately equal to 0. But actually, this one turns out to be quite a coarse approximation, and this is because even though alpha 0 might be low, then for the alpha harmonic, then the chirp rate is actually L times alpha 0. So that one varies much faster, and then the approximation is worse. And a point here is also that since both alpha 0 and omega 0 drive the instantaneous phase of all the harmonics, then all harmonics should also be used. And the methods derived for example, single sinusoids, for example, Jensen's method, they are actually not optimal for this problem. Okay, so let's now move on to try to derive an optimal estimator for the harmonic chirp model. To do this, first we define a matrix, or a vector rather, containing the observed signal going from xn0 up to xn0 plus n minus 1. And we call that vector x, and a vector containing the complex amplitudes called a here, where we have, as you can see here, the amplitude, the real positive amplitude for each harmonic multiplied by e to the power of j times the phase phi here for each of the harmonics here in it. And then we define a matrix set here, where we have a column vector here for each harmonic. So this is written as subscript omega 0 alpha 0, and you can see the definition of vector down here, that so if we have sets L omega 0 and L alpha 0 here, then you can see that it's just the chirp model for that particular harmonic, with the time matrix going from n0 to n0 plus n minus 1. Okay, so if we assume that the noise term, which was called E of n, in the model is white and Gaussian, then the maximum likelihood estimator is the nonlinear least squares estimator. And this means that we can find the parameters of the model by simply minimizing the 2 norm of x minus the matrix Z times a here, like this, over the parameters, namely the amplitudes, the fundamental chirp rate, and the fundamental frequency here. And since we're not really interested in the amplitudes by themselves, but more so in the chirp rate and the fundamental frequency, we can concentrate this problem here by solving for the the amplitudes, complex amplitudes rather, given alpha 0 and omega 0, and then substitute that solution into the equation. And in that case, we get this estimated down here, that we should we get the estimates of alpha 0 and omega 0 here by minimizing the difference between x and this matrix here, pi times x, and then this matrix pi here is simply the projection matrix for the matrix set, having the parameters omega 0 and alpha 0, like this down here. And this, of course, involves two-dimensional nonlinear optimization, where we have to find alpha 0 and omega 0. To find these parameters in a computationally efficient manner, we propose an iterative algorithm. And so we start with saying that, for example, omega 0 superscript I in parentheses up here denotes the estimate of omega 0 in iteration I here, and as you probably noted already, the hat indicates an estimate. So the idea is that first we obtain an estimate of alpha 0 denoted alpha hat 0 I from a previous estimate of the fundamental frequency, which has the superscript I minus 1 here, by maximizing the projection of x onto the space spanned by the matrix Z. So that's x Hermitian transpose times the pi matrix times x. And so when we do this, we maximize over alpha 0 only, and we keep the fundamental frequency fixed like this. And then once we've done that, we move on to estimate the fundamental frequency omega 0 using the same principle, but now we keep alpha 0 fixed. So we plug in the estimate of that we just obtained of alpha 0 here, which we call alpha hat 0 at iteration I, and then we again maximize the projection energy here. And then of course we continue this estimation back and forth, finding the chirp rate, finding the fundamental frequency until we have convergence. And you can do this in terms of convergence in terms of the cost function we have here, or in terms of the estimate parameters. Now, the fundamental chirp rate is expected to be low, while the fundamental frequency can be from 0 to 2 pi divided by L if you have L harmonics. And for short segments, we can expect the chirp rate to be small. So an idea here is that we can initialize alpha 0 as simply 0 and then estimate omega 0. And then this turns out to be the same problem as normal pitch estimation with the harmonic model. So we have good and fast methods for doing that. And well, also a comment about the model order L, because I've been including that on all the equations here, but I didn't really talk about it. But if you look at speech and audio signals, you actually need to find this model order L typically on a segment-to-segment basis, and that you can do in different ways, including the AIC and MDL and BIC criteria and so forth, which is completely consistent with what's going on here. Now, it's possible to implement the iterative method on the previous slide because they involve only one-dimensional searches, so that's relatively easy, even though there are nonlinear problems. And secondly, once the fundamental frequency has been found, then only small changes are expected. And I'll show you an example of a cost function later to show you why that is. And the way we do this in practice is that we do a local grid search in the area that we're interested in, and then we do a dichotomous search in a convex region to get refined estimates. And finally, I've been alluding to the importance of N0 at several points in this talk here, but George showed that you get the best possible estimates by selecting minus n minus 1 divided by 2 for an odd n to get the best possible estimates of the parameters. And not only that, you actually also get decorrelated estimation errors on the different parameter estimates, at least asymptotically so. All right, so before I show you any results, a bit about the experimental setup. So first, I'll show some illustrative examples, and then some histograms of differences in estimates to investigate the importance of this model here. Now, I'll do this based on 30 clean sentences from the noisiest speech corpus, and the non-least square pitch estimator is run on 30 millisecond segments in increments of 5 milliseconds, and it's done by first using a harmonic model and then the harmonic chirp model to find their parameters. And then we look at the differences in the obtained estimates, and this is only done when we are really certain that there's a pitch present in the segment, and this detection is done using simple GLRT with a low false alarm rate. All right, first off, here's an example of some spectra from the harmonic model, the harmonic chirp model, and this approximation that I said people have been using in the literature. And this is these models are then fitted to a speech signal, and what we see here is simply the first 5 harmonics here. Now, the blue one is the harmonic model here, and you can see you have the nice regular spacing here, and you can recognize the nice regular shape of the sinusoids like this. But once you get the harmonic chirp model here with even a relatively small chirp rate here, you can see that, well, the lower harmonics like this still have this nice and regular slope, but as you move up in frequency, you actually get more and more sort of a distortion or modulation of the sinusoid. And of course, this is to be expected since the chirp rate of the higher harmonics is L times the fundamental chirp rate. And in the red one, you see this approximation from the literature I talked about, and you can see that it's actually a really poor fit to the harmonic chirp model. you can see that it was supposed to be something that's an approximation of the green line, but it actually looks more like the blue one. So it's actually not a very good model, and it gets worse the higher you go in frequency. Okay, so here's an example of the pitch estimator we talked about here when it's run on a piece of voice speech that's continuously changing. You see spectrogram of the voice speech. It's all voice speech here, which really shows the non-stationarity of the speech here. And you can see that the fundamental frequency is really continuously varying. You can see that the harmonics here, the higher you go in frequency, the more modulated they are. And then when you take this method, the analysis method here with the harmonic chirp model, and run it on here, you can see you estimate these pitches here. You can see it captures quite nicely the contour of the pitch over time. Here's an example of what a cost function, the nonlinear least squares cost function, might look like as a function of the chirp rate here on the x-axis and the fundamental frequency up here. And what we're really looking for here is then the minimum of this cost function here, where in here we have the we have the global minimum here. But the point here really is that you can see that the cost function actually is kind of complicated. It is a nonlinear problem, and you can see that it's not nicely convex in a huge region around this place in here. In fact, you can see you have something up here, which appears to be another minimum in this cost function. I should say here that the cost function here is the 2 norm of the modeling error as a function of the different parameters here. Yeah, and this really shows you why this is a difficult problem, right? But it also shows you here that this idea of initializing the model with a chirp rate of 0 and then using that as a starting point is actually a fairly good one, because we will be in the region of the global minimum here. Good. So what you see here is a histogram of the differences in pitch estimated obtained with the harmonic model and the harmonic chirp model when run on real speech signals. So this shows what differences, the difference we can expect to encounter when applying the chirp model rather than the harmonic model. And what you can see here is that most of the time the differences are really small, which means that the harmonic model is good. But you can also see that there are actually differences in pitches here quite often that are in the order of a couple of hertz. And if you look at it from a psychoacoustic point of view, such differences in a fundamental frequency might actually be easily audible. So this shows the difference you get by using this model and this estimator with the chirp model rather than the harmonic model. Now, if we take and use the estimated parameters and plug them into a model and resynthesize the signal, then we can actually measure how well we reconstructed the signal. And the SNR improvement, so the improvement we get in reconstruction error is what you see here. So you can see here that most of the time the reconstruction error, the difference is quite small, but there are cases where you have differences that are on the order of a few dBs. One should also be a bit careful here in that speech and audio signals typically tend to have not so much power at the higher frequencies, which means that in terms of an SNR measure, these will not figure prominently, but perceptually they are quite important actually. So while these differences might appear small, they might actually be important. All right. So what we've seen here is that we have introduced a new model for taking the non-stationary nature of speech into account in pitch estimation. And unlike the models that's previously been used, this one is an exact model, a nonlinear model. It features a fundamental chirp rate and fundamental frequency. And the chirp rate then describes the change in the fundamental frequency. We've also proposed an estimator for finding the parameters, namely the fundamental frequency and the chirp rate. And this estimator was based on an alternating optimization principle. It's a non-convex and non-linear problem, but we could solve it anyway using this alternating approach where we initialize with estimates obtained with harmonic model. We've also seen here that a commonly used simplification of the chirp model appears to be quite inaccurate and inadequate. And as you've seen, simulations show here that we can get improved parameter estimates with this, and we can also get a better model because it fits the models better. That was it. Thank you.